Okay, so in this next chapter, we're discussing and we're really going to drill down into the idea of chemical reactions, predicting chemical reactions, and describing the behavior of species in solution. So just as a review, ionic compounds in aqueous solutions. So an aqueous solution, so water is our solvent. Soluble ionic compounds will dissociate into their component ions. So for soluble ionic compounds, you'll see them denoted with an aqueous symbol in aqueous solution. So for example, our sodium chloride, which is a soluble ionic compound, will break down into its component ions when it's placed into solution. So for example, we have our solid sodium chloride. The moment we put it into water, the moment we put it into an aqueous solution, we observe our component ions. So we have sodium plus and Cl minus chloride ion present in solution. Okay. Note that the number of ions generated per mole of ionic compound depends on the chemical formula. So just to showcase that analogy, let's suppose we are dealing with calcium chloride. What ions would calcium chloride break down into if it's a soluble ionic compound, if it's aqueous? What ions will we observe? And don't be shy to type in the chat. So what ions and how many of each ion will we observe? So I noticed people mentioned calcium. Okay, and how many chloride ions will we produce? 2, exactly right, exactly right. Okay, notice how the subscript indicates the number of each ion. So it's 2 Cl minus, not Cl2 minus. So remember to break your ionic compounds into their component ions. This will be critical when we discuss this idea of net ionic equations. Now I put this in all caps just because I see this a lot. Do not dissociate covalent compounds or polyatomic ions into their component atoms. Only break ionic compounds down to their component ions if they're soluble. Okay. Insoluble ionic compounds are denoted by a solid or liquid symbol, and they do not dissociate in aqueous solution. Okay, so for example, lead chloride. So if we were to draw a picture of lead chloride, let me see if I can find a silver color. Lead chloride would just sit as a solid at the bottom of your reaction mixture. It's insoluble. Does that make sense to everyone? The distinction between soluble versus insoluble. So if we look in solution, would you expect for us to observe a large or small amount of ions in this solution? If we have an insoluble ionic compound, would we expect to observe a large or small number of ions? Small, exactly right. Okay, perfect. So an example of a covalent compound would be like methanol, for example. An example of a polyatomic ion would be carbonate. These species you don't break down further because they're not ionic compounds. They're a polyatomic ion, which is a covalent species, and a covalent compound. So make sure not to dissociate covalent species into their component atoms. I see people do this a lot in net ionic equations, so you just always need to remember covalent compounds, you keep them together. Ionic compounds, if they have an aqueous symbol, if they're soluble, you break them apart. So just to really hammer home this idea of ionic compound dissociation, so soluble ionic compounds, so soluble, remember the aqueous symbol, dissociate to give their component ions in solution. The moles of ion per mole of ionic compound is based on the chemical equation, okay? So for example, 1 mole of sodium sulfide in solution gives 2 moles of sodium plus and 1 mole of sulfide. Okay, so if we look at our formula, Na2S, for every 1 mole of sodium sulfide, we know that looking at our stoichiometry, we have how many moles of sodium plus per mole of sodium sulfide. How many moles of sodium do we see in our chemical formula? How many moles of sodium do we see in our chemical formula? 2, exactly right, exactly right. And we read that from our chemical formula, okay? So really use the formula as your guide. And I'm just gonna show you this brief diagnostic. It's a little shortcut I've developed. So if we look at our formula, so Na2S. So first and foremost, each of your subscripts indicates the number of each ion. Okay, that's a nice trick to know. And additionally, if you cross the subscript over, this tells you the charge. Okay, so you can make a table. So for a 2-ion system, you can make a table. You read the subscripts, that tells you the number. And then you cross the subscripts, and this gives you the charge. This is just a nice procedural method if you want to indicate the number and charge of each ionic species in solution. Whatever suits your fancy, whatever you're comfortable with. Okay, so let's keep going. This is mostly review. Now, this is a table that you're going to have to memorize. This is a table that you're going to have to memorize. So this table on page 3 of the notes, you're going to have to become quite familiar with. This is our solubility rule table. So let's go through this piece by piece. So group 1A, if it has a group 1A ion, let's list a few of these. What are group 1A ions? So if we go to our periodic table, what are examples of group 1A ions? Would someone like to list one? Hydrogen's a bit special. Sure, francium. Let's try to list some of the more common ones. Sodium, yep. Okay, lithium, yep. Potassium. Okay, so all ionic compounds containing group 1A ions are soluble. Likewise, any ionic compound that has an ammonium salt is soluble. For our anions, we have acetate and nitrate. Acetate and nitrate salts are all overwhelmingly soluble. Okay. Halide, chloride, bromide, and iodide salts are soluble. There is an exception. There is an exception. Silver, lead, and mercury salts are insoluble. Okay? So for example, let's use red just to be consistent. Silver chloride would get a solid symbol because it's insoluble. So when you think insoluble, think solid. When you think soluble, I want you to think aqueous. Sulfate salts, for the most part, are soluble except for calcium, strontium, barium, and lead, which I label as insoluble. So for example, Lead sulfate would get a solid symbol. In general, the main offenders in terms of insoluble species have large ion charges. Okay, now we're going to draw a dividing line. And to do that, I'm going to make a dividing line in red. Okay, now we're looking at our insoluble salts. So these are insoluble salts. So carbonates, phosphates, and chromates are insoluble. Sulfides and hydroxides are insoluble. We know this in our day-to-day life because hydroxide and sulfide precipitation is the primary way that we remove trace metals from our wastewater, in fact. However, there are some exceptions. For our carbonates, phosphates, and chromates, the group 1A and ammonium salts are soluble. And soluble tells us we put what symbol? What symbol do we put for soluble? What symbol indicates soluble? Aqueous, exactly right. So group 1A, 2A, and ammonium salts for our sulfides are soluble. And for our hydroxides are group 1A and then calcium, barium, and strontium. Okay. Unfortunately, you are going to have to memorize these solubility rules, but many of these rules are redundant. For example, your 1A and ammonium salts are almost always going to be soluble. Now, things are best learned via practicing, so let's apply this solubility table. So let's write the state symbol for the following compounds and indicate the major chemical species in solution and the number of each ion produced if the compound dissolves. So you're going to help me out on this, and I'll start off with the first one. Sodium sulfide, okay? So I'm going to look at my table, and staring at my table, my question to all of you, sodium sulfide, does it match any of the ions on this list? Where should I look first? The group 1A column or the sulfide column? Where do you want me to start? 1A, okay? So I go to my group 1A column and I look and see, lo and behold, these compounds are always soluble. Okay, so I'm going to take my sodium sulfide and I'm going to put an aqueous symbol next to it. Okay, now I have to break it down into its component ions. Okay, sodium sulfide breaks down into 2 sodium plus, reading off from our subscript, and 1 sulfide ion. Okay, let's do another example. Barium sulfate, a commonly used imaging agent. So I'm going to go to the sulfate column. So I go to the sulfate column and reading off, looking, I find barium. My question to all of you is barium sulfate in the soluble or insoluble column? Soluble or insoluble? Insoluble, exactly right. So what symbol do we put? What symbol do we put? Solid. So do we break this barium sulfate solid into its component ions? Do we break this barium sulfate? No, exactly right. Okay, let's do one more. Aluminum hydroxide. Okay, so I don't see aluminum on my list anywhere. So let's look for hydroxide. And lo and behold, we find hydroxide. So do we see aluminum in our list of soluble species, or is aluminum in our list of insoluble species? Is aluminum hydroxide soluble or insoluble? Insoluble, exactly right. We don't see aluminum in our exceptions, so we get a nice solid symbol, and aluminum hydroxide does not dissociate. Wonderful. Okay, you're going to need to have this solubility table handy for the majority of today's lecture. Okay, so I'd like you to write the state symbol for the following compounds. You need to indicate the major chemical species in solution and the number of each ion produced. So I'll leave you to work first and foremost, and you're free to ask questions during this time, but let's work on these first four. Oops. Let's work on these first four, and you're welcome to submit your answers via the chat. So let's start by working on these first four, and then we'll come together as a group to discuss in a few minutes. And you're welcome to message me your responses during this time. This is a critical skill that you want to practice using your solubility table. And don't be shy to message me with your response for each of these compounds, whether they're soluble or insoluble, and what ions are generated in solution. And let's try to get some responses in the chat, just reading the table. And I'd just like you to tell me for each of these four compounds individually, which species are soluble, which species are insoluble, and what compound and what ions do we generate in solution. So let's take a few more minutes to work through this, and then we'll come together as a group to discuss. But I do want to see some student input, just so that way I know that you're comfortable using the solubility table, which is on page 3 of the notes. Does anyone have any questions so far working through this problem? So let's provide some guidance now, and then I'll let you loose on another batch of problems. So sodium nitrate, okay? So I go up to my table and I see it has a group 1A ion, it's just sodium, and it has a nitrate ion, and both of those are soluble. Okay, so sodium nitrate gets the aqueous symbol, and we dissociate sodium nitrate into sodium plus aqueous and NO3 minus aqueous. Okay, let's look at aluminum chloride now, and let's figure out what state symbol we need to put. So we go up to our solubility table once again, and we find chloride. Do we see aluminum in our soluble or insoluble column? For aluminum chloride, do we see aluminum in our soluble or insoluble column? Wait, so chloride, bromide, iodide, all of those are soluble except for silver, lead, or mercury. So do we see aluminum in our soluble column or insoluble? Is it soluble or insoluble? And to answer this question, is aluminum silver, lead, or mercury? Is aluminum any of these exceptions? No. Ergo, aluminum chloride would be soluble or insoluble? Is aluminum chloride soluble or insoluble? It's soluble because it's in the soluble column and it's not one of the exceptions. So then aluminum chloride would get an aqueous symbol, and aluminum chloride breaks down into, oops, it's just, would break down into aluminum 3 plus and 3 chloride ions, reading from the chemical formula. Okay, let's do one more. Calcium phosphate, Ca3PO4 2. So let's go to our table. And we found phosphate. And looking at our list, phosphate salts in general are insoluble with a few exceptions, So, is calcium on the list of exceptions? Is calcium on the list of exceptions? No. So then, is calcium phosphate soluble or insoluble? Insoluble, exactly right. So calcium phosphate gets a solid symbol, and as a result, it doesn't dissociate. Okay, potassium acetate. Let's look at our table once again. So looking for potassium or acetate, we find 2 hits. My question to you is, are acetate salts soluble or insoluble? Are acetate salts soluble or insoluble in general? Looking at our table, soluble, exactly right. So they get an aqueous symbol, and we break potassium acetate into its component ions, which is potassium plus and acetate, which has a -1 charge. Perfect. Is this making a little bit more sense now that we did a few more examples? Is everyone comfortable with this idea? Okay, I am going to need to check. So what I'm going to ask for you to do is to attempt the following 3 examples and tell me whether they're soluble or insoluble, and list the major species in solution. So let's take about 2 to 3 minutes to work on that. And I'd really like to see some messages from students in the chat, just so that way I can get a sense of whether anyone has any questions and how comfortable everyone is with this idea. Because if you can't identify species as soluble or insoluble and write the ions in solution, it'll be very difficult to write net ionic equations. So let's take a moment to work on that, and then we'll come together as a group to discuss in 2 minutes. Yep, marginally, that's a reasonable response for silver chloride. Let's get a few more responses in the chat and spend about another minute reading through our table and discussing this problem. Yeah, so let's take a look at all of these. So cobalt sulfide. So let's go up to our table once again. So looking at sulfide, are sulfide salts in general soluble or insoluble? So we found sulfide. Are those salts in general soluble or insoluble? And I see a lot of people are replying that they're insoluble. Exactly right. So we're going to put a solid symbol. Cobalt sulfide does not dissociate. Okay, let's look at lead chloride, PbCl2, or lead 2 chloride to be exact. Chloride salts in general are soluble. Do we see lead on the list of exceptions? Do we see lead on the list of exceptions? Is lead chloride soluble or insoluble? And I see a few insolubles in the chat. That's exactly right. So lead chloride gets a solid symbol and we do not dissociate it. Finally, let's do silver chloride. So let's go to our chloride or halide column. Chlorides in general are soluble. Do we see silver on the list of exceptions? Is silver chloride soluble or insoluble? Let's take a moment and read the table and let's see what we conclude. Insoluble. Yep, exactly right. So it gets a solid symbol and we don't dissociate it. Perfect, perfect. Okay, so let's now apply this idea and let's talk a little bit about acids and bases in aqueous solution. So acids and bases are covalent compounds that are typically soluble in water. So we'll see the aqueous symbol a lot for acids and bases. Now, the critical thing about acids and bases, for that matter, is that they dissociate to generate ions in solution. So acids can be thought of as a proton donor. For the perspective of net ionic equations, they dissociate to give H+ and their conjugate base in solution. Okay, so they're generating ions in solution. So if we think about, for example, a bottle of hydrochloric acid. So if we look at a snapshot of a picture of hydrochloric acid in solution, we'd expect to see primarily ions. So we'd have H+ and our conjugate base of chloride, Cl-. So we have ions in solution. Okay, we've seen this idea before. Let's look at bases now. So bases are an H+ acceptor. From the perspective of net ionic equations, bases will react with water to give hydroxide and their conjugate acid in aqueous solution. That's one potential way that bases can generate ions. So for example, sodium hydride reacts with water to make hydroxide and hydrogen gas. That's one mechanism of base behavior. The far more common, and the one that I want you to focus on in this chapter because it comes up way more often in net ionic equations, is that bases will dissociate to generate hydroxide in solution. So our strong bases are soluble ionic salts containing hydroxide. So I want you to see page 3, the page 3 table. So these are our group 1A barium, strontium hydroxides. reading off from our page 3 table for solubility. So just like when we drew a picture for our acid, if we look at a flask of sodium hydroxide aqueous, we'd expect to see primarily ions in solution. So we'd see our hydroxide ions and then our corresponding sodium cation. Of course, surrounded by water molecules, but we won't be worried about the solvation for right now. Okay, so strong bases, just like strong acids, dissociate completely in solution to give mainly ions in solution. So we've seen this before from our discussion of acids and bases and ionic compounds. Any questions so far? Any questions so far? So just keep in the back of your head, strong acids, strong bases, mainly ions in solution, they dissociate completely. Okay, really critical. Okay. So weak bases are compounds containing an amine functional group. And the one thing I want you to remember for your weak bases, give me one moment just to reset the view. Okay, so the one thing I want you to remember for your weak bases is they dissociate less than 1% in solution, and we have mainly dissolved molecular compound in solution. So let's draw an example. So let's suppose, we have a typical basic amine, such as, for example, methylamine. Allow me one moment to restart OneNote. Give me 1 second just to reset OneNote. Okay, so let's suppose we have a basic amine such as methylamine. For the most part, this basic amine will remain as whole molecular compound in solution. So if we look at a picture of methylamine in solution, although it has the aqueous symbol, what we will see overwhelmingly are molecular species in solution. We may see a very, very small number of ionic species, but for the most part, we have primarily dissolved molecular compounds. And as a result, so for weak bases, do not dissociate weak bases when writing ionic equations. From the perspective of ionic equations, a weak base primarily exists as a molecular species. We do get a little bit of ionization, but it's negligible from the perspective of ionic equations. Does that make sense to everyone? Does this idea make sense? Everyone comfortable so far? Okay, let's keep going now. Okay. So let's look at strong acids and weak acids. So strong acids, so this is your nitric, perchloric, sulfuric, hydrochloric, your halogen acids. These dissociate completely in solution, and we see mainly ions in solution. So for example, if we have sulfuric acid, which is a strong acid, it will break down into H plus protons and the conjugate base anion. So if we looked at a picture, of a solution of sulfuric acid, we'd see overwhelmingly that we'd have ions in solution. We'd have almost only ions in solution. There would not be any dissolved molecular compound. Okay? So strong acids, you completely dissociate. So weak acids, however, are any acid not listed as a strong acid, and they dissociate less than 1% in solution. So for weak acids, we have mainly dissolved molecular compounds. So a classic example of this is acetic acid. So acetic acid, it's an acid. It is soluble in water, but in terms of what species we actually see in solution, if we look at a picture of acetic acid, we would have primarily molecular compound. So we'd primarily have our acetic acid molecules floating around in solution, and we'd maybe see a very, very small amount of ions. From the perspective of ionic equations, for weak acids, do not dissociate weak acids in ionic equations. So weak acids and weak bases, do not dissociate them when you're writing an ionic equation. Okay, perfect. So here's a table of the common strong acids and common strong bases. You are expected to be familiar with these, and you'll need these to write reasonable ionic equations. Okay, so we've overviewed the solubility symbols. So let's tie this idea of solubility under this one umbrella that we call electrolytes. So electrolytes refers to this idea that ions dissolved in solution conduct electricity. Okay? So our strong electrolytes, they dissolve and completely dissociate to give ions in solution. These are your strong acids, strong bases, and soluble ionic compounds. So let's give an example of each. So let's look at a strong acid. Would someone like to give me an example of a strong acid that we have not yet discussed today? Or just any strong acid that you can think of that, yeah. Let's see some responses in the chat. Nitric acid, sure, that's a good one. HNO3, it's a strong acid, it gets the aqueous symbol, and it dissociates to yield H+, and nitrate ion. So if we drew a microscale picture, I always like to draw pictures since it's easier for me to rationalize and understand a picture than words, at least makes it easier to remember since it has all these nice bright colors. So we'd see primarily ions in solution. Note in these drawings, I'm being very careful to also respect my chemical formula stoichiometry. Now, really important, does everyone notice how we keep nitrate together? Remember, this nitrate is a molecular ion or polyatomic ion. Please do not break nitrate up into individual atoms. Please do not do that. I see this happen a lot when students are introduced to this idea of ionic equations. Just remember, if it's a polyatomic ion, keep the molecular compounds together. Keep them together, okay? Nitric acid breaks down into ions, but nitrate doesn't break down further. Okay. Let's keep going and let's look at a strong base. So would someone like to give me an example of a strong base? Calcium hydroxide. Let's check our list. Yep, that would work. That one I had to check just to be 100% sure. Perfect. Okay, and this one's interesting actually. I really like this example. So we break it down into calcium 2+, and how many hydroxides do we generate? How many hydroxides do we generate? 2 from the chemical formula. Don't forget these little details because they matter a lot. Okay, so if we're drawing a picture, let's draw our picture down here. So we'd have calcium 2+, and then of course we'd have our 2 hydroxides. Does this make sense so far to everyone? Let's keep going. I always like to draw pictures, makes things easier to remember. Let's look at a soluble ionic compound. Would someone like to provide me a soluble ionic compound for us to discuss today? There are hundreds of potential options, so there aren't many wrong answers here. Can we propose a different one just because we've discussed sodium sulfide already today? But that is a wonderful response. That's perfect. Let's try to get a little more variety, just so that way the notes have a pretty diverse range of examples. Would someone like to provide us an ionic compound that's soluble that we haven't discussed today? Sure, perfect. Lithium sulfide. Okay, so has a group 1A element, so it's going to be soluble. Remember, see table, just if you want to be sure. Oops, give it one moment. Okay, so lithium sulfide is going to break down. Oops, allow me one moment just to reset OneNote. Okay, perfect. Let me just zoom back in. And just as a refresher, for lithium sulfide, so lithium sulfide is going to break down into its component ions. So in this case, we'd have 2 lithium plus and S2 minus, both of which get the aqueous symbol. If we're drawing a picture, of lithium sulfide, we'd see our lithium plus and then our sulfide ion in solution. Notice how I drew 2 lithium ions per sulfide ion. Wonderful, wonderful. We're doing well so far. So let's keep going with this idea now. Weak electrolytes, so weak electrolytes, and let me use the corresponding color for that. Weak electrolytes, they dissolve and then they partially dissociate less than 1% in solution. So for weak electrolytes, we have mainly molecular compound in solution. These are our weak acids, weak bases, and slightly soluble ionic compounds. We're just going to put a star next to this one because the idea of slightly soluble ionic compounds is brought up mainly in Chem 102. Okay, so just like before, so for weak electrolytes, you do not dissociate weak electrolytes in ionic equations. Okay, so would someone like to give me an example? Let's give an example of a weak acid. Let's give an example of a weak acid. So what's an example of a weak acid that we have not discussed today? Just to keep things a little bit interesting. A weak acid that we haven't discussed today. Hydrochloric acid is a strong acid. Citric, sure, that would work. Do you have the formula for citric acid handy? Could I have the formula for that? I can look it up momentarily. Let's do hydrogen sulfide for now. So for our weak acid, so we have H2S, aqueous, and we draw it as an equilibrium. It could technically break down to yield H plus and bisulfide anion. But in reality, if we drew a picture of our weak acid, for the most part, we'd see mainly our molecular compound in solution. So we'd see primarily our hydrosulfuric acid and maybe a trace amount of H plus and bisulfite anion in solution. Okay, so in general, do not dissociate weak electrolytes in ionic equations. So just to round out this discussion, just as review, would someone like to provide me the formula of a weak base? What's an example of a weak base? What's an example of a weak base? Ammonia, exactly right. Exactly right. So ammonia can react with water to generate a small amount of ammonium and hydroxide. Yep, that's always a possibility. But if we look at a picture of ammonia in solution, so if we were to draw a picture of ammonia in solution, we'd primarily, overwhelmingly observe molecular compound. So we'd primarily see our ammonia, and we may see just a little bit, less than 1% of this ammonium and hydroxide ion. So we have mainly molecular compounds in solution. Okay, wonderful. So let's look at another category of species. So these are primarily what we call non-electrolytes, and these are primarily where we see our covalent compounds that you need to be careful with. So our non-electrolytes, they dissolve, but they do not dissociate. So we have primarily and almost entirely dissolved molecular compound in solution. We have no ions present. Okay, so what type of compounds make up our non-electrolytes? These are soluble covalent compounds containing an OH, NR, CO or SH functional group. So examples of this that we come across pretty regularly in our discussion are alcohols. Oops, one moment. One moment, let me do a quick reset. So the most common non-electrolyte that you'd observe, at least in the laboratory for this course, would be your alcohols. So that has this OH functional group, an example of which would be methanol. It is soluble in water, but does not dissociate. So if we look at a picture for this non-electrolyte, what we would see is 100% molecular compound. We'd only see our methanol floating around in solution. We would not see any ions. Okay, other examples of non-electrolytes would be something like acetone, which again has this carbonyl functionality. You don't have to memorize all of your non-electrolytes. The majority of the non-electrolytes that you'd see in this class are going to be alcohols of some variety or thiols of some variety. The main thing I want you to keep in mind for your non-electrolytes, so non-electrolytes do not dissociate. Okay, so now that we have this idea of electrolytes and what the major species in solution would be, there's one other distinction that I like to use when describing strong, weak, and non-electrolytes. I call this not available. It indicates that the compound does not dissolve in aqueous solution. So these are insoluble or immiscible compounds and insoluble ionic compounds, just to be explicit. So for water immiscible compounds, you're primarily dealing with compounds containing only carbon and hydrogen. So let's give an example of an insoluble ionic compound. What's an example of an insoluble ionic compound? And there are a lot of them, but let's try to list at least one of them for our discussion. What's an example of an insoluble ionic compound? Sure, lead chloride, that's good. So if we look at a picture of the solution for lead chloride, we'd overwhelmingly just see our solid lead chloride at the bottom. And we'd see a negligible amount of ions in solution. So in terms of immiscible compounds, in terms of an example for an immiscible compound, these are hydrocarbons, compounds containing only carbon and hydrogen. So an example would be C6H6, which is benzene. We know intuitively, for example, that oil and water do not mix. I like to think of these immiscible hydrocarbons as like oil. They're really greasy, they're very non-polar, and they don't mix readily with water. So for example, if we mix benzene and water, we end up with a heterogeneous solution. So we have our water, and then as a separate layer, as a separate clearly visible layer, we have our C6H6. So we would write for an immiscible compound, these are liquids, so they get the liquid symbol. They do not dissociate to yield ions, and they are not dissolved in solution. So immiscible, not mixable liquids. So that's why we give the liquid symbol for immiscible compounds and the solid symbol for insoluble. Does that make sense to everyone? Okay, so let's keep going. Let's keep going. We've covered all of our major state symbols. So what we're now going to do is we're going to predict if the following compounds are strong, weak, or non-electrolytes or not available, indicate the major chemical species in solution if the species is soluble. So I'll do the first one. So CH3OH. So it's an alcohol. So this is a non-electrolyte. So we write this as CH3OH, aqueous, and it does not ionize. It does not dissociate to yield ions in solution. I'll do one more, sodium nitrate. So sodium nitrate, so I see it's a sodium salt. So immediately I know it's a soluble ionic compound. Ergo, it's a strong electrolyte. So we'd write this as the aqueous symbol, and it would dissociate to yield sodium plus aqueous and NO3 minus aqueous. Strong electrolytes dissociate to yield their component ion. Okay, copper sulfide, CuS. So I know that sulfides, for the most part, are insoluble. So this is an insoluble ionic compound. So I denote this as not available. It gets a solid symbol, but it does not dissolve. So there's nothing in solution. Does this make sense so far to everyone? So to check that everyone's comfortable with this idea, I want you to tackle the next 3 examples. I'd like you to tell me whether they're strong, weak, or non-electrolytes, and I'd like you to identify the major species in solution. So let's take about 2 to 3 minutes to work on this, and then we'll come together as a group to discuss. And don't be shy to communicate in the chat any of your assignments for these 3 compounds, as they're strong, weak, non-electrolytes, or if they don't fall into any of those categories. Any questions? Don't be shy to ask questions in the chat. We'll spend about another minute on this problem, but I do want to get some student responses just to check that everyone's comfortable with this idea. Okay, so let's discuss, and I'm going to ask for your input here. So ammonia, so NH3, is it a strong, weak, or non-electrolyte? Strong, weak, or non-electrolyte? And to answer that question, okay, I see a lot of people typing that it's a weak base. Okay, since it's a weak base, that tells us that it's a weak electrolyte. Okay, so we put an aqueous symbol, and my question to you is, for the perspective of ionic equations, would we have mainly molecules or mainly ions in solution? Mainly molecules or mainly ions? Molecules. Yep, exactly right. So we have mainly molecules. Okay, potassium hydrogen sulfate, which is KHSO4. Is this a strong, weak, or non-electrolyte? And to answer this question, what is potassium hydrogen sulfate? Is it ionic, molecular, is it an acid, is it a base? What is it? Yep, it's an ionic compound. And is it soluble or insoluble? Now you're going to have to go to the solubility table. I'll give you a hint. We see this wonderful potassium ion. So is it soluble? Yep, exactly right. So then this soluble ionic compound gets an aqueous symbol. It's a strong electrolyte because it's a soluble ionic compound. And it dissociates to yield its component ions of potassium plus and hydrogen sulfate ion. Okay, so we have ions in solution. Okay, let's take a look at another example, C5H10. So this is a hydrocarbon. What type of compound is this? Is this soluble, insoluble, miscible, immiscible? How would we classify C5H10, which sort of reminds me of oil? Yep, it's an immiscible. It's an immiscible, so we classify it as Na. And because it's immiscible, miscibility, C5H10, we typically view it as a solid or a liquid. Solid or a liquid. Liquid, yeah. Hydrocarbons are overwhelmingly liquids in the context of chemical reactions that you'll see in this class. You aren't expected to memorize whether a hydrocarbon would be a solid or a liquid. I'd give you a hint on that. Okay, there are a few more examples, but we'll skip those because I see everyone's pretty comfortable with this. In the last about 12 minutes of this class, we're going to introduce and talk a little bit about this idea of ionic equations. So the main point of ionic equations is to really understand what chemical species are actually reacting. So chemical reactions may involve only some of the ions from the dissolved ionic compounds. So for example, we have our chemical equation that we are so used to seeing. A total ionic equation dissociates all strong electrolytes into their component ions. Okay, so to give you a sense of what's going on here, we took our sodium hydroxide and we broke it down into sodium plus and OH minus. We took our hydrochloric acid and we broke it down into H plus and Cl minus. And I'm putting the aqueous symbol throughout because you really want to be careful with your state symbols. Our sodium chloride, we also dissociated to yield sodium plus and Cl minus. Perfect. And after breaking down each of our ionic compounds, we wrote out all of our ions into our ionic equation. Okay. There's a special indicator, special word that we use for ions that do not participate in the chemical reaction. We call these spectator ions. So these are ions that do not react in a chemical reaction and do not change in charge or physical state. So keep this in mind because we're going to approach redox reactions, which are reactions where the ion can change in its oxidation number, change in its charge. So you want to make sure you're not just checking that the ion is unchanged in physical state, but also that it has the same oxidation number or charge. Okay. Ultimately, our goal when we write net ionic equations is to begin to write what are known as net ionic equations. It's a chemical equation that indicates the physical state of all ions, molecules, and compounds that participate in a chemical reaction. Notice, what I mean by participate in a chemical reaction is the net ionic equation does not include spectator ions, which are just spectating. They aren't participating actually in the reaction. So for example, in our ionic equation, we notice that our sodium plus and chloride ions are unchanged in physical state or charge. So these are our spectator ions. As a result, when we're writing out our net ionic equation, we simply get rid of and we cancel our spectator ions. And that in turn gives us this simple net ionic equation, which helps us understand what is actually going on in our chemical reaction. Fundamentally, this is an acid-base reaction. H plus and OH minus are reacting to yield water. Okay, that's the theory. Let's talk about the practice. How do we actually write net ionic equations? How do we actually write net ionic equations? That's our goal. So our goal is to be able to write net ionic equations. Okay, so step one, you write the chemical equation and formula of each species in the reaction. Okay, so that's our first step. Then we balance our chemical equation. We've done that before. Now is where things get interesting. You're next going to have to dissociate all soluble ionic compounds, denoted by an aqueous symbol, strong bases, and strong acids. So this is where you're going to need the table on page 3, as well as the table of strong acids and strong bases. You're then going to write your total ionic equation. Once you have your total ionic equation established, you're going to identify all of the spectator ions. They have the same physical state and charge before and after the reaction. And then all you're going to do is cancel all of the spectator ions. So for example, if you have a sodium plus on the left-hand side and you have a sodium plus on the right-hand side, you're just going to cross them out. Note, if you have one chloride on the left and you have two chlorides on the right, you're only going to cancel one chloride. Does this idea make sense? Just like mathematically, like 1 is equal to 1, you can subtract and you can just easily say 0 is equal to 0, right? You can only cancel ions that are present on each side, and you only cancel the amount that's present on each side. Finally, you're going to write the net ionic equation. So once you've canceled the spectator ions, your equation's almost done. Well, let's do some examples. So I'm not having you write the formulas just yet. Let's just focus fundamentally on the state symbols. So we're going to fill in the state symbols for each reactant and product. We're going to write a balanced chemical equation, total ionic equation, and net ionic equation. Okay, so let's start procedurally and let's get a balanced equation. Let's get a balanced equation. Is this equation balanced currently? Is this equation balanced currently? No. Okay. So what element do we want to start with? What element do we want to start with? What element do we want to start with in balancing this equation? And let me adjust our view. Okay, let's start with iron. Okay, so let's just do a tally. So first things first, I'm going to write each of my reactants and products. So we notice in terms of our tally, we have 2 irons on the left. We have 1 iron on the right. So 1 times what would give us 2 irons? What coefficient do we need on the left? 2. Perfect. We now have 6 chlorines. Okay. And we also have 3 sulfurs on the right. We have 1 hydrogen and 1 chloride as well on the right. So let's balance chlorine now. So what times 1 would give us 6 chlorines? What coefficient goes in front of hydrochloric acid? 6. Okay. So now we have 6 hydrogens and 3 sulfurs on the right. So we have 2 hydrogens and 1 sulfur. What coefficient do we need to multiply our 1 sulfur by to get 3 sulfurs? What coefficient do we need in front of H2S? I see someone typing 3. That's exactly right. Perfect. So we've balanced the equation. Now let's put our state symbols. So hydrosulfuric acid, is that a strong or weak or non-electrolyte? Hydrosulfuric acid, H2S, is it a strong, weak, or non-electrolyte? So this is actually a weak acid. Sulfuric acid is the strong acid. Hydrosulfuric is a weak. Either way, since it's an acid, it gets an aqueous symbol. Okay? Okay. Iron 3 chloride, FeCl3, is that a soluble or insoluble ionic compound? Is it a soluble or insoluble ionic compound? Iron 3 chloride. Soluble or insoluble? And don't be shy to flip to your table. It's soluble. Yep, that's exactly right. So it's an ionic compound. I like to put these little labels on top just to help me organize my thoughts. Iron 3 sulfide, is this soluble or insoluble? Iron 3 sulfide, soluble or insoluble? Remember our discussion of sulfide salts? Sulfides, are they in general soluble or insoluble? And don't be shy to flip to your table. Insoluble, exactly right. So we get a solid symbol. Hydrochloric acid, is that a strong or weak acid? Exactly right, it's a strong acid. So we put the aqueous symbol. Okay, now that we have our balance equation with our state symbols, now what we're going to do is we're going to dissociate each of our soluble ionic compounds, strong acids, and strong bases. So then, for hydrosulfuric acid, since it's a weak acid, do we dissociate it when writing an ionic equation? Do we dissociate hydrosulfuric acid? Do we dissociate it? Yes or no? No. The reason, it's a weak acid. Okay, do we dissociate iron 3 chloride? Do we dissociate iron 3 chloride? Yes. So then we multiply each of our subscripts by our reaction coefficient. That gives us 2 iron 3 plus. Remember, because if we take FeCl3 and we cross our charges, that gives us iron 3 plus. Aqueous, how many chlorides do we generate? How many chlorides do we generate? How many chlorides? 6. 2 times 3 is 6. Do we dissociate iron 3 sulfide? Do we dissociate iron 3 sulfide? Nope. It's an insoluble ionic compound. Do we dissociate hydrochloric acid? Do we dissociate hydrochloric acid? Yes. And we get 6H plus and 6Cl minus, aqueous. Now we identify our spectator ions. So what ions are identical in charge and physical state on each side? What ions are identical in charge and physical state? The chlorides, yep. So we can just cancel them out. And that gives us, for our net equation, 3H2S aqueous plus 2 Fe3 plus aqueous leads to iron 3 sulfide and 6H plus. This really lends this to the idea that some metal ions are quote unquote acidic in character because they can react with certain weak acids to generate a strongly acidic solution. Okay, I'm planning for this laboratory period to lecture in laboratory, just so that way we're on pace to finish the content by the end of the semester. I will see everyone in laboratory in about 10 minutes. So I'll see everyone in lab at 2:32. And just as a note, remember all the lectures are recorded and posted on our course channel.